Good morning and welcome to this first lecture on vibrations of plates and shells. We will be discussing vibrations of continuous systems. What do we mean by continuous systems? You must have seen at some stage or the other a course on lumped vibrations. Okay, 1 degree of freedom, 2 degree of freedom systems. This must be familiar to you. So here I have a spring and a mass system. The spring constant is k and the mass has mass m. Okay. Now this is a lumped system. What do you mean by lumping? This mass here has no springiness, okay, and this spring over here has no mass, okay, there is no inertia associated with it. Okay. So similarly, if you have a damper, it only damps vibrations proportional to velocity. It has no other fundamental properties associated. Okay. And therefore, when you have such systems, the number of degrees of freedom is finite. So you have this is a 1 degree of freedom system, because you will locate this mass using just one coordinate, and so the degree of freedom is finite. Okay. Now in theory of machines or as a separate course somewhere, you must have seen vibrations of a beam. Okay. So here is a cantilever beam I am showing. Here I have shown with some thickness, and here I have shown it as just a simple line. So it is built into the wall here and it vibrates. So it vibrates, let us say, like this. The tip has the maximum deflection. Okay. So you must have seen this sort of a system somewhere. So what is the difference between this and the spring mass system on the left? Here at every point within the medium, within the material, there is inertia, there is stiffness, there is damping. That means the density is a function of x. Okay. It is not that I have lumped the mass at one point, the stiffness at the another point, and so forth. No. So such systems are continuous systems. Okay. And what is the result of that? The result of this is that the number of degrees of freedom are infinite. So you have an infinity of resonances and mode shapes. Okay. That is what you have to deal with. Now, as I have mentioned in the introduction to this course, we will begin by looking at some simple things like curves, okay, tangents to curves, curvatures, okay, radius of curvature and the curvature vector. Then we look at planes, we will look at surfaces, properties of surfaces, we look at normals, okay, and how curves and their properties relate to surfaces and their properties. Okay. This topic actually is part of a much bigger and deeper course called differential geometry. So we will just skim through maybe the first 2-3 lectures. Okay. So here is a coordinate rectilinear orthogonal coordinate system. These are the basis vectors E1, E2, E3. Okay. And in our familiar form, these are x, y and z, and here is a curve in 3D, a curve in 3D. Now let us say there is a point and I would like to denote the point, okay, and let us say the curve is parametrized in terms of a real variable t. Okay. What does that mean? T is a real variable that varies on the real axis. real number axis between say 2 points A and B. Okay. So, the t moves between 2 points and is a real number, and the curve we are discussing is parametrized. That means every point is given in terms of t. Okay. So, that means what, my r of t is given by some function of t, let us say f1 of t plus f2 of t plus f3 of t. Okay. The vector r is given like this. Okay. Now, suppose I want to look at another point delta t later. Okay. Delta t can be anything and it can be time also. Okay. T can be just a variable or t can be time. If it is time, we get a slightly more physical meaning to the properties. Okay. So, now if I say that I have another point t plus delta t later. Okay. So, this first one is r of t, the second is r of t plus delta t. So, if I draw it here again, I have this delta r of t. This is r plus delta t, this is delta r of t. Okay. So, that is also a vector, that is also a vector. So, delta r of t, if I divide by delta t, okay, and I take the limit delta t tending to 0, if I take this limit, then you can see that in the limit I have delta r becomes very small, okay, and delta r by delta t assumes a tangential direction, okay, and it approaches what, dr dt, dr by dt, the value approaches dr by dt. Now, if t is taken to be time, then dr dt becomes velocity. It is tangential to the curve and it is physically the velocity. Okay. Now, in here we have this arc length, okay, we have this arc length and we have this chord length. Okay. So, the thing is, what is the arc length? What is the arc length? What is the arc length? Okay. We will arrive at it from the chord length idea. The chord length delta r is equal to delta r magnitude by delta t into delta t. Okay. So, in the limit, this is equal to r dot of t into delta t. Okay. And as delta t is sent to 0, the chord length approaches the arc length. And so to get a finite arc, okay, so to get a finite arc length, a finite arc length, what we do is limit n tends to infinity summation, let us say I goes from 0 to some n minus 1 delta I Ri magnitude, which is equal to limit n tending to infinity summation over I 0 to n minus 1 magnitude, okay, which is equal to finally integral a to b r dot of t dt. This is the arc length between t is equal to a and t is equal to b. Okay, we will give it the symbol S, or between R A and R B. Okay. Let us now take an example. Let us take an example. The example is a helix. Okay. Let us take a helix, helical curve. The R of t is given by cos of t I plus sine of t j plus tk. Okay. This helix is parametrized in terms of the real variable t, and t can vary between 2 points A and B. Okay. So if I draw this, how does it look? If this is my xy plane, then the first part gives me a circle. Okay, the first part gives me a circle, whereas the k part gives me a progression in the z direction. So I get a helix like that. Okay, I get a helix like that. With t increasing, it moves like that. Okay. So now I can talk of r dot of t, okay, which is minus sine t plus cos t plus k. Okay. And this describes the tangent at every point on the curve. Okay. And so if t happens to be my time, if t is my time, suppose, okay, then the magnitude of r dot is equal to the square root of r dot of r t dotted with r of t, which is equal to square root of sine square t plus cos square t plus 1 is equal to root. So this is the speed, at any point. Okay. And what is the arc length? Arc length in one circle, okay, 1 2 pi rotation. What is the arc length? Okay, that S is equal to integral 0 to twice pi. See, t is time, t is also the angle actually. Okay, so that is equal to magnitude of r dot of t dt, which is equal to integral 0 to twice pi root 2 dt is equal to 2 root 2 pi. Now, so far we have parametrized in terms of a real variable t. Okay, t could be anything. What we are going to now do is parametrize in terms of the arc length S. Okay, so what is arc length? Arc length S between points t equal to 0 and t equal to t, let's say, is 0 to t, magnitude of r dot u du. Okay, so let's see for the same helix. Okay, so example, for the same helix, which is what? Which is initially in terms of t cos ti plus sin tj plus tk, okay, at t equal to 0, r of t is 1I. Okay, so the arc length between t is equal to t0 and t is equal to some t is what the arc length is. S is equal to integral 0 to t magnitude r dot u du is equal to integral 0 to t square root cos square u plus sin square u plus 1 du. Okay, that gets me integral 0 to t root of 2 du is equal to root 2t. Okay, so now we have a relationship between the parameter t and the arc length S. So if your curve is parameterized as t, you can convert to s and vice versa. So, in this case what my s is equal to root 2 t, or t is equal to s by square root of 2. Okay. So, if I now substitute it here, substitute it in the expression with t, I get my r hat of s is equal to cos s by root 2 I plus sin s by root 2 j plus s by root 2 k. Okay. The reason I take this, put this extra hat on it, is because the expression itself is different, and I put s instead of t. Here I have cos d, here I have cos s by root 2. The form is different, form has changed, and so I put a hat on it. I put this hat here. Okay. So, now the curve is parametrized in terms of arc length, s. Okay. So, now if we have r of t is given. Okay. How to convert? How to convert to a function of arc length? Okay. My s is equal to integral 0 to t magnitude r dot u du. Let us say that is f of t. Okay. So, now we solve for t from s. We have s is equal to f of t, and we solve for t. Solve to t is equal to g of s, let us say. Then we substitute. Okay. Then we substitute for t and get r hat of s is equal to the original r of g of s. Okay. Okay. So, now there are some interesting things here. So, now s of t is known, written as 0 to t r dot u du. Okay. Now, we take the derivative. It is a function of t. So, we take the derivative with respect to t. Okay. What do we get? We get s dot of t is equal to magnitude r dot of t. Okay. So, you see now what is s dot? S dot is the rate of change of arc length, and r dot of t was velocity vector. So, r dot of t was velocity vector, the tangential velocity vector, and therefore the magnitude is indeed the speed, which is s dot of t, the rate of change of arc length. Okay. Now, the question we ask is, if this is how the curve is, and let us say from here to let us say here, this happens to be my delta S and this happens to be my delta R. Okay. So, what is R hat of S d by ds, right? What is this? This is the limit as delta S tends to 0, delta R by delta S. Okay. So, now as this goes to smaller and smaller values, let us see, as my arc becomes smaller and delta R becomes smaller and delta L becomes smaller, delta S and delta R magnitudes approach each other. The numerator is a vector, denominator is a scalar. So, this approaches my t, which is the unit tangent vector, Okay. So, I will put this arrow on it to indicate the unit tangent vector. Do not confuse it with the real variable t. Okay. So, what do we say? We say dt, just hold on. Okay. So, we have the unit tangent vector t. Now, what we do further here is to look at what is curvature. What is curvature? Or radius of curvature. Okay. So, these are questions we will ask. Time is run out. So, what I will do is I will stop the lecture here and continue from this point in the next lecture. Thank you.